This video is for Lesson 70, solving direct variation problems for my pre-algebra classes. So in our last video, we talked about direct variations. And remember, the whole idea behind a direct variation is that we have a relationship between two different sets of values, where what you do to one value, you do to the other. So if you double one value, you double the other value. You cut one value in half, you cut the other value in half. So today we're going to look at solving some problems that are direct variations. So first of all, if we take a look at this from the standpoint of a table of values. So, and we're just going to do this real general. So we've got our first x value, x sub 1 is our first x value, and that pairs up with our first y value, y sub 1. X sub 2, then there's our second x value, that pairs up with our second y value, y sub 2. And obviously, symbolically, we could continue this forever, however long we want. The idea behind a direct variation is that there's this constant relationship here. Remember k, where k equals y over x. So y over x, kind of like slope is rise over run. So in this case, this would be y sub 1 over x sub 1, and this would be y sub 2 over x sub 2, and likewise, we could continue this on forever and ever and ever. Well, remember that each of these is equal to k. So therefore, if we take this idea right here, one of the things that we can do to solve direct variation problems is to use our values to construct a proportion. So one of the big things that we do when we have direct variation problems to solve them is we make proportions. That is one method of solving direct variation problems. Now, excuse me, another idea coming from this is if k equals y over x, if k equals y over x, I'm going to switch it around and make it y over x equals k. Okay. Then we can take this and, using some algebra, construct the equation y equals kx. And so this is a second thing that we do to solve direct variation problems, is we can instead make equations. Now, it's helpful here to have the real-world connection. Realize that k is the rate, or if we're talking about a graph, the slope. So if you're given a rate or a slope, you know that's going to be your k. Now, if we consider having an equation, we can imagine our slope-intercept form, which also draws the connection that slope is our k is our slope. So slope is m, but in this case that's k. Now, if this is slope-intercept form here, though, we're not adding anything. So not adding anything is the same as plus 0. So that means that in this case, our y-intercept is 0, 0 because b is 0. So that means if I want to, if I think it would be helpful, I can actually make a graph of my direct variation. So we know all direct variations go through the origin, and they have a slope of k, which if we think of k as being k over 1, that means if I rise k, however much k is, then I will need to run 1. And so this right here would be another point, and I'm going to send my line through them. And this is a third way that we can solve direct variation problems, is we can make graphs. Today we're going to look at some practice problems, and in particular, we're going to focus actually on these first two methods here today. We're not going to worry about so much about making graphs, but we're going to focus more on the first two. So if you would grab your books, please, and open up to, I believe for you it is page 473. 473. We're going to take a look at some practice problems together. So here we go. First problem. The distance a coiled spring stretches varies directly with the amount of weight hanging on the spring. If a spring stretches 2 centimeters when a 30-gram weight is hung from it, how far will it stretch when a 75-gram weight is hung from it? So here's a couple things that we want to kind of take into consideration. First of all, what do we want to be our input and what do we want to be our output? So whether we're looking at the proportion, this doesn't matter a ton, but it can be helpful as well. But especially if you're going to make an equation, we want to consider input versus output here. So look at the question. How far will it stretch when a 75-gram weight is hung from the spring? So if I consider a table of values here for just a second, I'll make a simple table of values. In a moment here, we're going to want to be able to plug in 75 grams. So I want my input to be the number of grams. Now what I'm going to get out of that should be the answer to the question. So how far will it stretch? Well, if you look at previously in the problem, we're measuring that in centimeters. So how far will it stretch? I don't know yet. But that distance I want to be my output. So grams will be my input and centimeters will be my output here. So, and we're going to go ahead down here for problem A. So my X value in grams, and then my Y value in centimeters. And the problem is asking 75 grams stretches at how many centimeters? So here we go. We'll solve it first using a proportion. So for the proportion, Remember, the proportion is going to be a y value over its corresponding x value equals a different y value over its corresponding x value. So remember that y is the centimeters. So if we look back in the problem, we knew about 2 centimeters being how far it was stretched when we put on 30 grams. Okay. And then now I have my unknown. Since this is there, let's just stay clear of x and y this time. I'm just going to call my unknown a here. And so I don't know how far it will stretch, though, when 75 grams is put on yet. So there's my proportion. And we can go ahead and solve. Now, one of the things that catches my eye on this, which could be helpful or not, but 2 and 30 could be reduced. So that is an idea. Now, if I don't reduce it, I'll have 2 times 75, which will turn that into a nice 150. So you could reduce this, you could not reduce this. Right now, it's up to you. I'm going to choose not to. I kind of like the 2 times 75 making 150. So if I go ahead and multiply, cross multiply, I'm going to get 30a, and then my other cross product will be 2 times 75 is 150. Now to solve this, we simply have to divide both sides by 30, and now that's a nice easy problem. So a therefore equals, well, 30 goes into 150 5 times. Now, since this was the output value here, the y value, it is in centimeters. So if we put a 75 gram weight on it, how far will the spring stretch? 5 centimeters. There's my answer. Now we're going to do this problem again, but this time we're going to use the equation to solve it. So in order to do the equation is y equals kx. So first of all, we need to figure out what k is. Well, k is going to be equal to any y value over its x value. So that's my first step. K, and remember, it equals y over x. Well, again, we've already determined that y is going to be our number of centimeters. X will be my number of grams. So the problem said that if the spring stretches 2 centimeters, the spring stretches 2 centimeters when a 30 gram weight is hung from it, well, then my 2 centimeters over my 30 grams, that will be my k. So a little reducing there real quick. K is 1/15. So now my equation, y equals kx. Well, k we just figured out is 1/15 and x. So if I want to solve the problem, now we just got to plug in this 75 for x. So y equals 1/15 times 75. Now, ladies and gentlemen, I've taught you this before, and if you can remember it, it's a nice little trick. That whenever you have a whole number times a fraction, treat the numerator as if you're multiplying that with the whole number. Treat the denominator as if you're dividing the whole number by it. So 1 times 75 is just 75, but then 75 divided by 15, some of you might have that memorized, is 5. And of course, y is measured in centimeters. And there we go. Now, the nice thing about the equation is, once we have the equation down, if you needed to then find out how far would it stretch for an 80 gram weight, how far for an 82 gram weight, how far for a 46 gram weight. Once you have the equation, it's a whole lot faster. Just keep plugging in successive value after successive value over and over and over again. Whereas using a proportion, proportions are really just one and done. You plugged in your corresponding values, you solve. There's not a lot of reuse here. You could set up a new proportion to solve for a new value, but it'd have to be a new proportion each time. Whereas over here, this is just nice and simple because, well, you just have to plug in your x value to find the next y value. All right, let's go on to B. So let's flip our papers over. I think we're all kind of running out of space there. So if we flip over to B here, B, the number of words Tom types varies directly with the amount of time he spends typing. If Tom types 100 words in 2.5 minutes, how many words does he type in 15 minutes? Okay, so again, I'm going to come back over here and I'm going to do a little bit of thinking. So I'm going to think about if I got a table of values, what do I want to plug in? So look at the question. So the question here is saying, how many words does he type in 15 minutes? So, excuse me, I want to be able to, when I'm done, plug in 15 minutes and find out how many of what for the answer. So if I'm plugging in 15 minutes, that means that my x value is going to be in minutes. And then we're finding out how many words. So this will be words for my y value. So I'm going to put this on my paper here real quick for you. So x is going to be in minutes, and then y is going to be in words. And our final question here of this problem is asking us 15 words, or excuse me, 15 minutes is how many words. So again, we're going to solve this using a proportion, and we're going to solve it using an equation. So for our proportion, we already know that Tom types 100 words in 2.5 minutes. So our proportion, go back over here, y over x, y sub 1 over x sub 1 equals y sub 2 over x sub 2. So I'm going to put my, my words over my minutes. So I'm going to put my 100 words over my 2.5 minutes, and that then is going to equal my unknown words. I'll just call it A again. Wasn't a great A, let me fix that. That's better. Over my 15 minutes. Now, if you want to do some reducing before multiplying there, you could go ahead and try to do that. I might actually do a little unreducing. Give you another option here. I'm looking at 2.5, and maybe I don't like that decimal, but I recognize that 0.5 is a half. So instead of dividing the top and the bottom by the same thing, how about we multiply the top and the bottom by the same thing? So if I multiply the top and the bottom here both by 2, this will become 200, but this will become 5. And now I don't have to deal with a decimal anymore. So for that matter, now you could go one step further, and you could do some reducing before reducing here. So 200 over 5, you know that 5 goes into 20 4 times. So 5 must go into 200 40 times, and 5 goes into itself once. Now if I cross multiply, I've got A times 1. Well, 1 times anything is itself. So 1 times A really is just A. And then over here, I've got 40 times 15. Now, you all should remember 4 times 15 because we think of our clock. So if you got 4 groups of 15 minutes, well, that's a full hour. That's 60 minutes. So 4 times 15 is 60. Then 40 times 15 should be 600. And remember that this is our unknown, what we're trying to solve for, so it is in words. So Tom can type about 600 words in 15 minutes. For my equation, remember we start with K, and K equals Y over X. So the Y value that we know, the words we know, is he can type 100 words over the corresponding minutes is 2.5. Now, if you simplify this, and you could even just grab a calculator for this guy, you'll come up with the answer 40. So therefore, my equation, y equals kx, well, k we just found out is 40. So if you want to find out what y is, take the value of x and multiply it by 40. Well, in this case, we're trying to figure out what happens when x is 15. So we're going to make it 15. And as we just did, 40 times 15, well, 4 times 15 is 60. So 40 times 15 is 600. And they both work. And we'll go ahead and finish off the last practice problem here. We'll do C. So for C, traffic was dense for the evening commute. Mitchell traveled 3 miles on the highway in 15 minutes. Predict how much longer it will take Mitchell to reach his exit 5 miles away. So, assuming that he's traveling at the same rate, which this problem doesn't actually say, but we're going to go ahead and assume that because that's certainly what they intended. So we want to consider again, what's my input, what's my output. I'm going to skip the dry erase board here. So look at the question. So predict how much longer it will take Mitchell to reach his exit 5 miles away. So we know we're going to want to solve something having to do with 5 miles. So x is going to be in miles. And there's going to be 5 of them. Y though? Okay, so how much longer? Well, if you look at earlier in the problem, the length of time was measured in minutes. So y will be in minutes. And we don't know how much longer yet. So we're going to solve this one twice again. By the way, on the homework, no, you do not have to solve it using both of these. Pick one. I would even encourage you to, on different problems, try one method on one problem, try a different method on a different problem. Okay? But it is okay to have a favored method here. That's perfectly fine. So when it comes to the proportion, this is going to be minutes over miles. So we already know that he has gone 3 miles in 15 minutes. So y over x, minutes over miles. So that'll be his 15 minutes over his 3 miles equals his unknown number of minutes over the 5 miles left he has to go. All right, well, obviously, I can reduce that fraction. I'm going to do that. I like making my life easier. So 3 goes into both of those. 3 goes into 15 5 times. 3 goes into itself once. Now, if we cross multiply, 1 times anything is itself. This is another one that's going to work out very nicely for us because it's just going to be A. On the other side, 5 times 5 is 25. Now, remember that this is measured in minutes. So Mitchell has about 25 minutes left to go. For the equation, remember that K always equals the Y value over the X value. So My y value that I knew was 15. My x value that I knew was 3. So this is 15 thirds. In this case, fractions mean division. Just divide this. 15 divided by 3 is 5. So my equation then, y equals 5x. The x value I want to know about is 5 as well. So therefore y equals 5 times 5, which is 25 minutes. And that, ladies and gentlemen, is our lesson.